I forgot to start the video. Sorry, I just started the video. I'll post the thing or email it to everybody. That's what I'm going to do. Okay, so yes, definitely disconnect today. Okay, so if we take a look at this tester.c, it's got this fill macro. And what fill does is create functions here that calculate something based on our input. And we want to have 10 functions for this array. And so fill here will go ahead and make them all. So there we go. It makes a returners whatever, and they all get put into this returners list here. Okay. Is there anything else about this one? I guess that's about it. Does that make sense now? I didn't talk a lot about the macro. You didn't have to do anything with the macro either. I mostly put it here because there's macros used in the kernel, and so I figure, why not? I'll show you another macro here. You can see one then. See what they do. Okay, so let's see. I guess that's about it for that one. The other ones are pretty straightforward. I didn't have any questions on the other ones. Questions on the assignment? Okay. They're just looking at like, what did you do again? There's it. That. There's other ways to do it. The first time I solved it, I actually did it differently. I'm not sure where my solution is. I emailed out something like this last time I taught the class too. And I think last time, instead of casting it that way, I cast it as a void double star. And so then when it was a void double star, I went through it one void pointer at a time, and then individually cast each of the void pointers to the right function pointer type. And that works fine too. Yeah. Okay, so hopefully that'll be around at some point, and go through and grade these things, and yeah, each of them's worth a third, so I figure the curve will come out probably just fine, because I bet most people got the first one, piece of cake. I'm going to bring my hard drive up here. Oh well, maybe next time. Okay, so what else am I supposed to talk about today? Oh, I just posted Project 2, and Project 2 is a simulated file system, like it says. And I'll let you read this thing for yourselves, but let me show you what the project looks like. I have it on here? Yes. It is solved. No. That's fine. Good. Okay. So I've got these kind of three entities here. And so the relationship here, you got a tester that does the testing. And so the tester calls functions in the file system, which calls functions on the drive, the hard drive. And so there'll be a simulated hard drive that you write a file system for, a real file system for, and then there'll be a test program that checks to see if your file system works. If you look at the header here, the file system has to support 4 operations here. You can save a file, and if you're saving a file, you get a char star, a file name there, a string. And so the string has a name, and then you have some data, and you have a size for the data that's going to be placed in there. Now, there's also some errors this thing can return. And so if this works, it should return 0. It's kind of a standard convention for C programs that 0 indicates everything was fine, and a non-zero number is used to indicate an error. And so this will work that way. And so this one can return a name conflict. Go ahead and name that, or a no space. There's not really a not found for save. And in load here, take a character pointer again, because you got to file name to load. And then this void star, which is the location to store the data. And so this will read the file and copy it into the area indicated. Now the third third parameter here indicates the maximum amount of data that your file system should put into this area. And so if the file is bigger than that, then your file system shouldn't keep dumping data into this spot, because you're going to cause some sort of memory error. There's no more space. And so you should read all that space. As much of the file can be read as should. And then the return value will be no space. And so this would actually allow the user of the file system here to get the first part of a file, like basically run the head program, and get the first so much of it, because they just say, this is how much we're going to read, and then that's how much you have to read. Okay, and then we got a f-delete. This deletes files, and so that removes the indicated file, and it can return not found error. And then you can format it. And so this one will get called, I guess it doesn't, strictly speaking, have to do anything, but it'll get called by the test program before the test program tries to store files on it. Also, if you format the file system, that should get rid of all the files. And I think the test program does test that. Okay, so that's the only 4 things that have to be done. A couple of rules in fs.c here. Oh, this is my solution. Wait, why didn't it work then? Oh, it said good on all of these. Okay, that one's already solved. I think I have the original one somewhere.
So now all we have to do is watch the video and pause it at that moment to see your solution.
Well, yeah, the first part of it.
That's like comments anyway, so it probably wouldn't help too much.
Well, yeah, you can go find the leading comments on it. That'll be fun.
Or like pull it up and then scroll down.
Okay, so here's the how this thing starts, and you don't have to keep the names in here if you don't like them. The return 5 is just a placeholder. It has to return an integer because it says it'll return an integer. And these are just in here so that the project will compile. So, in terms of storing data, your file system has to store all your data on the hard drive. It can't keep any data around from one function call to the next. So, you can't use global variables or static variables to store data, or contrive some other method where you keep everything outside of the disk. Everything has to go on the disk. Okay, so the disk itself, and this is where I was going to bring, let's actually get drive.h. Okay, so there's number of cylinders, number of sectors per cylinder, number of bytes per sector. This is where I was going to bring on a hard drive, and I'll just show you a picture. There's some risk to pulling up Google Images in class, but usually works okay. Okay, that's like big. I click on it a couple of times. It'll get smaller. And if I make it smaller, it gets smaller. Okay, so that's what a hard drive looks like. I might still bring it up and pass it around. I think most of you have seen one at some point or another. So you got this platter here, and it spins around. And you got a head on the disk that moves back and forth. And it's got actuators and stuff on it. And so if your hard drive fails, a lot of the time it's some kind of mechanical failure involved in this stuff. Sometimes it's the control circuitry on it. Anyway, so you got this whole thing here. It's a dust-free environment inside here because it's under a cover, and a sealed cover. And it's divvied up into concentric circles. And so it's not like a record. A record has a spiral from the center out. And so you can put the needle on, I guess it goes in as the record player plays. But spiral. This one has concentric circles. And so it's divided up into sectors on each of these concentric circles. And so, circles. And then, you got a spindle in the center. One more circle. Okay. So then you got divisions and sectors here. Okay. And the geometry has to be a little bit more complicated than that in some cases to try to maximize efficiency here. Because obviously there's going to be more drive in this sector than there is in this sector. Things started out more this way, but modern drives have matured a little bit. Anyway, I visualize it like that. Also, most drives have a stack of platters on them these days. And so you can have like multiple all stacked up. But basically this one's divided up is you got cylinders, and then you got a number of sectors in each cylinder, and So this is straight up and down cylinders from one platter to the next. And you got a number of bytes in each of the sectors. And there's macros to figure out the cylinder size and total sectors here. Is this the actual solve one? No, it's the start one. Okay, and so you've got two things you can do in order to manipulate this drive. You can read a sector or you can write a sector, and that's it. And when you write a sector, you need to provide a void pointer here, which will be the area for the memory to be written. And so these have to be at least bytes per sector in size. And so it'll go ahead and read, bytes per sector data from that. And there it goes. With no further checking. Okay. 0 indicates success. It can return a bound cylinder or bad sector if these ones are specified out of the range for the drive. This doesn't mean that it's going to pretend that sectors have gone bad on the drive. It won't. The simulated hard drive won't fail. That might have been a fun thing to add.
Random failures.
Yeah. Okay. So there's yeah. Okay, simulated hard drive implementation. Is this the finished one or not? Anyway, this one has the read sector and write sector, and so this is the drive implementation here. And there's not really anything in particular that you need to do in this file. I'm just showing you that they're there. This is where the actual hard drive is stored. Like, it's coming down to the simulated hard drive. There isn't a simulated. This is actually storing its data in main memory. And so the place that stores it is just a big area that's malloc for the drive. And yeah, there we go. Okay. So, in terms of the test it has to pass. So there's kind of a list of them here. But it just kind of goes along and tests something, and it'll print out some feedback. It's certainly possible to make a file system that doesn't actually work, but yet somehow passes these tests. Now, there's kind of a spot check on it, but I think they cover most of the cases. And if it works in a regular manner and pass all the tests, that's good. Okay, well, I'll let you read through the instructions and things, and hopefully that'll make some sense of it. Hopefully it'll be a fun project. Yeah.
When is it due?
I forgot. Monday, October 12th.
Which chapter are we supposed to check?
Chapter?
In the book.
Oh, for this one?
Yeah.
Oh, you can read the links and implementation of the file allocation table.
Okay.
It's not really that well covered in the book. If you go on Wikipedia and read how file allocation table system works, that'll be fine. Okay, notes today. Okay, oh yeah, so kind of we've got to wrap up on the file systems. And I forgot to bring my hard drive, so apologies on that. Okay, so the hard drives, we took it at Project 2, and I want to look at the file systems just a little bit more, and then we'll get into how to boot up a computer. Okay, so there's a file allocation table system in the Linux kernel, and it'll be longer than the one that you have to write. If I look at P2 here, and everything.c, it looks like my file system was 229 lines. And as you noted, the entire first screen is comments and stuff, so it's not really that long. If we look at Linux kernel, Linux source 3.16, FS, that, it's going to be bigger, about 7,000 something lines. And so I took kind of a scavenger hunt on here. What's a table entry in the file allocation table system? Well, take a look at the header file. So there's only one header file in here. And if we look at it, it's got some structures defined and such. And so the first one up here is for mount options. And this is going to store some stuff at mount time and stick around for that purpose. Here's a super block info. Super block on a file system, and you might end up needing to use one of these probably. The super block contains the information about the rest of the file system. where is everything going to be located and whatnot. It's not necessarily required that you have one for every single file system. In general, it's going to be easier if you have a super block because it's convenient to have some place to store all the parameters that have to do with the drive somewhere. And a common place to put this is just sector 0, track 0, right at the very beginning. And right at the very beginning, you can read in what exactly is all the stuff that's required. Okay, so that's what goes into a super block. So like for a file allocation table system, in a simple sense, you want stuff like where the directory start, where is the root directory, and that kind of stuff. Okay, and there's a bunch of stuff that have to do with whatever. Dirty here means that something has been changed in file system terms. And so it'll get marked dirty if there's some change to the file system that hasn't been written to disk. And so they say FS state before mount there. Well, if they're mounting the file system and the dirty bit is set, so there's something that's been changed in the file system but it hasn't been written to the drive yet, then you got some kind of problem and should probably run a consistency check or something on it. So anyway, that's what goes into a super block typically. And you have inode info here, and this explains what is required for an inode, an entity that I guess is kind of, well, we can talk about what inodes are. Anyway, so there's what it's required for an inode. If you keep scrolling on down here, eventually you get to an entry in the file allocation table. And so the entry here has basically a pointer and indicates where its stuff is, and has a pointer here to an inode struct, which says what's stored at the particular location. Okay, I believe this pointer here can be used to figure out the location on a disk, and then you can figure out, okay, which inode is at this location, and from the inode struct, you can figure out, well, what's the file name and stuff like that, because that's going to be available in there. Okay. Oh yes, that's the answer to the scavenger hunt there. That's what goes in there. So in terms of the way these things are usually put together, and probably the kind of thing you'd want to copy, if you visualize the hard drive in a linear sense instead of like that, just kind of a linear set of places, you usually want to have some kind of super block that tells you, how big is the table, where's the end of the table, that kind of stuff. And then after that, a common thing to put is the actual table. Well, you don't know how many sectors a table is going to be. And so this actually provides a little bit of a challenge here. Because the table, you can keep adding sectors to the table as more files get added. And the fraction of the drive that's taken up by the table is related to the file size. Because if you have a drive with a whole bunch of little tiny files, you're going to end up with a lot of table in order to store references to all those files. A few big files, you won't end up with as much. Okay, and so anyway, you got a table there, and then after that, the rest of it is files. And if it's a pretty efficient file system, this will be most of the disk. And actually, Project 2 does have a test in there to see if your file system's efficient enough. It has a pretty low bar for efficiency, but it does check to make sure it can fill it. I don't know, I think it fills it calls it good if it fills it up more than about 70% or so. But anyway, so that's kind of a typical drive layout. Okay. Oh yeah, and I wanted to show you something kind of funny here. In this file called NameI, MS-DOS, it's got a function here that formats an MS-DOS file name and rejects invalid names. So in the DOS days, you can have 8 characters in a 3-character extension, and there was stuff you couldn't have. For example, you can't have names that start with a dot, and somewhere down here, it's got a place where it rejects if it finds a space. Where was that? I think it's somewhere in here. It doesn't all fit on my, there. So if you got a space or a colon or a slash in your file name, then it's an invalid file name. And it needs to be rejected. So anyway, it goes through all of these. And actually, you can see the same kind of pattern here. Like if you get to the bottom and it worked, you return 0 for success. And if it didn't work, return E inval, actually negative E inval. I'm not sure what a positive result means for this function. You can see it returns an int. And so it may have some condition here that returns something positive. Anyway, returning a negative error is a great trick for if you got some kind of function and it's going to return like the number of bytes read if everything went fine, and that could be 0, and then you make all your error messages negative, and it gives some more space for return results. Anyway, I don't actually see a positive result that this thing can return, but it might be that it's just set negative because of standard convention for this part of the kernel or whatever.
I don't think you noticed it was actually a really old file at the very top because it was written when it was written.
Well, yeah, you don't need to rewrite it. And code isn't like a car or something that wears
Well,
out.
it was rewritten in '99.
Yeah, for constant I numbers. Yeah, by Alvira. Yeah, now code doesn't really go bad in the wear out sense. It does have issues with future proofing, and so there's actually a fair number of tools where they still support 32-bit and nobody's bothered to update them, and so I guess they are worn out in some sense. This is a 32-bit program here because it supports FAT32. I don't think there is any FAT64. So okay, and the compiler can take care of a lot of stuff. Like you can compile this on a variety of architectures and it'll come out right. Okay. Oh, and I want to talk about layer file systems real quick too, because layer file systems are always interesting. Okay. So this is how a file system works if you're storing something on a disk. You come up with some kind of organization, tells you where all the files are, and you put the actual files there. A layer file system operates over an existing file system. And so the principle here is that when you make some kind of call, like open, in your program, open goes down here into kernel space, and then before it gets to the file system, it goes through this layer, which does whatever it wants and then calls to the underlying file system. Okay. Layer file systems can be handy if you're trying to add features to a file system. And so I'll show you an example here where we're adding access control list support for file systems that don't already support that. Okay. I think I only have it on here. There it is. Okay. So I'll show you the general principle here. Okay, that's probably impossible to read. Okay, should be an open call in here. I think it's there's a prototype for it. Let's check access denied, etc. The open call is pretty short in this, and it kind of provides a good overview of what actually goes on. I can't seem to find it here. There it is. Okay. So this is for BSD. This is to go into the NetBSD kernel. And BSD family of operating systems calls an inode a vnode. And so when you see vnode, just think inode. It's basically the same thing, just BSD terms. Okay, so I got this struct Bob OpenArgs, whatever, and we got this check and bypass macro. And so this open function gets called if the open has been called on a file in our file system. And so you say, the user space level open, such and such, gives some file path. It's in the area that's part of this file system. This function here will get called, and it'll have a requester to open the associated vnode. Okay, now this check and bypass macro. Okay, we're giving it a layer open and 4. Okay, let's go see where this thing is defined. Right there. So what a check and bypass does is it calls ACLFS check access, and does some credential verification on the request. And if there is appropriate access, it returns a 0, no problem. And so then you go down here and return X, whatever was specified there. That was the function. It was layer open, down open when I looked at it. And so I call that function on whatever the vnode was. And so if it returns an access problem, and this will give you an access error, e-access. Okay, so let's take a look down here. Well, most of them do this, like ACLFS Open does it, and read and write and that kind of thing. Will do the same sort of stuff. And so there we go. That finds basically just checks access and passes on the request. The ACLFS check access function is kind of longer. This one actually has the what is in a VOP enumerated. That's convenient. Okay, so the general architecture of this thing is probably going to be easier than going through and reading it. Basically what it does is you take your file system as a tree, and slash is like the root of the tree, and so you got stuff on here. Well, if you got some kind of place on here, say this is MNT and this is CD-ROM, you can take this spot and mount it somewhere else, say slash CD-ROM. Okay, and so whatever tree is down underneath this thing over here, this is our CD's file tree, is going to get duplicated over here. And so what we'll see over there is a different tree. And so this tree is the same stuff, so I should draw it with the same branches. This it is the same files, but when you try and access one, you go through ACLFS, and then ACLFS will pass the request on over here. This area is going to be accessible only to root, typically. It can vary, but suppose you want to protect it. Say you got some users on your computer, and you trust some of the users to see the contents of the CD drive and not others. So then you'd say, okay, well this part here, this is chmod, so only root can see it. Root owns the directory, and it's like 700 or something. Okay, so then over here, you chmod this one's something else, like maybe 755. And so then users can go in here and make a request. So then you can come back to the same case here. You're going to allow some files and deny others. So ACLFS makes another file, and I think it usually just goes in /etc. And so this other file over here is the access control list. And so the access control list can have entries in here. Basically, such and such user is allowed to do such and such with such and such file. And so you can state exactly which users have access to exactly which part of this file system over here. And this, of course, is something that only root can access that too. So that's what it does. Okay, now this layer file system concept, can be used for a variety of purposes. This is just one of them. But this works. Code runs. It slows down file access a little, because like on that open thing, for example, open is going to be calling using this macro up here, check and bypass. Remember macro, you see it and you think cut and paste. So all this code goes down there. And it calls ACLFS check access. Okay, and so ACLFS check access, does all this stuff. You gotta go through the ACL and look for a matching rule, and check to see if there's anything relevant, and go through and process it and things. So it takes a moment for this function to run, and so it does slow down file system operations significantly. I don't remember how much exactly. I remember it was actually kind of dreadful.
I don't know if you said it in the past, but what kind of file systems is that software running?
It's running XFS. I was going to check and see. I probably have a table in here that shows exactly how slow it was. That doesn't matter. Here's the BSD usage. Russians usage and such. Oh, there's the benchmarks. Okay. NullFS, I think that's actually a layer, or no, that's, yeah, it's actually a layer that does nothing, as in just pass things strictly on. And so you can see it has almost no performance penalty. ACLFS, on the other hand, whatever benchmark I was using, takes a lot longer. Because 0.9, you know, it's like, that's terrible. That's like 20 times as long. So it took a lot more time. Okay. Oh, is there questions? Make sense? Okay. Here, so if you ever have to write a layer file system or use one for something, now you know what they're for. I've never really wanted ACLFS for anything in particular. I haven't run the code since I wrote it. I wrote a paper on it. Sent it to Usenix and they didn't like it because it was slow. Okay, so we're going to talk about boot up process. And so that's the next thing. We get to start the textbook now, which is great. Okay, so the boot process, it's named the boot process. It's short for bootstrapping. The idea is that you lift yourself up by your own bootstraps. And so that's what the computer does. And there's no particular problem with this concept. You just keep loading more and more of the kernel, and so the kernel kind of loads itself. There's pieces. There's an initial boot sector and things. Well, I'll go through it. The basic idea here is you're going to load bit by bit, get the operating system going in a more and more complete manner. Okay, so the BIOS does the initial setup, and you guys probably remember playing. Probably played with BIOS sometime, right? I see some nods and some not. Okay. BIOS is a chip on the motherboard. I should have brought a motherboard up here. And it's usually kind of hard-coded. You can flash these things and update them if you want to, but it's generally considered read-only memory. It's not something you change every day. And so the BIOS contains enough instructions to have the motherboard find the devices that comprise the computer and start to load the operating system. And stands for Basic Input Output Services or something like that. Okay, there's a more advanced one called UEFI that has a bunch of extra features. Stuff like connecting to the machine remotely using the network port and diagnosing it. And it's taken off. You kind of still see both of them to some extent, although UEFI is definitely taken over. It can be more difficult to work with just because it's new and people aren't really used to it yet. Yeah?
BIOS is usually only keyboards, but I've heard of some people being able to use their mouse in the newer ones.
Yeah, I just put in more instructions. Yeah, yeah. It's the BIOS back in the day. Yeah, it was usually just keyboards, but mouse support's been incorporated into them for a little while. There's no reason you can't. You can put whatever you want to in this in the BIOS. It's just that it's going to require more memory to have more support for more devices, and so flash memory is pretty cheap these days. There's not a lot of reason not to include support for NICE and stuff.
Last time I had to use a BIOS was on a laptop from 2009 that ran Windows 7, and it didn't actually have I don't think you could use the mouse. I think you can't use a keyboard.
Okay. Yeah.
I know with mine, I can't use my mouse correctly, but
Yeah.
I never have to get into it very much. Last time I had to do it was to enable virtualization.
Uh-huh. Yeah, that's the usual reason to go in there. That or to change the frequency of your CPU.
Yeah, I think I originally had to get in there when I first started up my machine to make sure everything was turned on right and have the auto overclocker set on and whatnot.
Yeah. Yeah.
Doesn't the AMD processors make you go in and work the BIOS for your RAM? Because I know Intel will automatically do it, but AMD needs an adjustment.
I always end up going through those settings to verify them anyway and set them to what I think they ought to be. I don't really know.
Yeah, ever since I had a motherboard over voltage my RAM, I look at that.
Yeah,
Because it killed a couple sticks of RAM.
yeah.
Can't you put a system password in the BIOS too?
Yeah, you can. Yeah, you can put a password in the BIOS such that you can't boot the machine if you don't know the password. And the only way around it would be to clear all of the settings that have been made into BIOS. And so to do that, you'd open up the case, and usually there's a jumper in there that you can use to clear the BIOS.
Yeah, which is why if you have physical access, it's kind of null and void point.
Right, right. If you steal somebody's computer, you can usually work out a way to boot it once you open it up and get to the hard drive contents and things. Hard drive encryption is the only thing that can really defeat the person with physical access. And even then, it can't have the key stored on the hard drive in an accessible manner. It's got to be a key you remember, something that's not in the computer. So yeah, that's what BIOS does basically. Go through and load all that stuff. And so that's why people use it to overclock their CPU, because you can tell BIOS that, why don't we just run the front side bus frequency 10% higher, and then your CPU goes 10% faster. Go fast, die quick. Anyway, I usually run mine overclocked. Okay, so UEFI is replacing it. Servers take forever to boot. Software takes like 5 minutes to boot. It's just got this elaborate RAID controller that has to go through and figure out everything that's attached to it. And then it puts together the 7 drives and a hardware RAID for /home. And it's got a fairly substantial process of figuring out what exactly it is every morning. People do that sometimes too. I mean, sometimes people wake up and they're like, okay, what is my name? Where do I live? Where's the coffee machine? You know, sometimes people do that. So anyway, the computer is the same thing. Okay, so it loads a little bit of hard drive onto the in-domain memory and starts it running. And so usually what you want to load is a bootloader. Now, when we go through the book in a minute here, it will actually load Linux directly with no bootloader. The reason that you want a bootloader is to manage startup options, basically. So if you think about a computer with a single hard drive, multiple hard drives, different case, single hard drive, and you're going to have multiple operating systems on here. Okay, here's your drive, and that's the boot sector up there. I drew it small because it is small. And then you got 2 operating systems here, A and B. Okay. What the BIOS will do for you is load this boot sector off into main memory. And so it'll stick it in here somewhere, and then it'll start it running. Basically set the instruction pointer to the first thing in this, this set of instructions and start running this code. And so what this code has got to do is get either operating system A or operating system B up and running for you. And so usually the code here will have some kind of selection dialog or something like that, where you can say pick an operating system or none of the above or do something else or that kind of thing. And so that's what a bootloader is for. Now, strictly speaking here, you don't necessarily need a bootloader in the sense that we do these things now. Because if you don't have this situation, if you just got one operating system on your hard drive and you need to start it, then all this bit of code here needs to do is get this operating system A running. And that's the situation that we're going to see with the Linux 0.11 kernel. It didn't really support having other stuff on the same other operating systems on the same disk. Incidentally, it also booted from floppy. So this back when that was how computers booted. Okay, so the bootloader, as far as what it does, there's a couple of them that are kind of common. Lilo is a Linux loader, and this is a real basic bootloader, and it can load Linux or it can load Windows, basically. And so it was a common thing to set up when you got A versus B like that. When you use Lilo, Lilo actually keeps enough information in this boot sector to get your kernel up and running for you. And so this involves copying something from your kernel, header for the kernel basically, to this boot sector so that it'll go into main memory. So, if you change kernels, you need to update what's located in the boot sector on your hard drive. And so Lilo has a program to do that. So the process, if you're updating your kernel, you set up the new kernel, and then you change Lilo's configuration to explain that there's a new kernel there, and then you run Lilo. Let me show you real quick the how you configure Lilo. So we're just kind of getting across the general point. I don't expect you to actually use Lilo because it's kind of old, but as you're about to see, I actually have Lilo on here. I can't even look at it as a regular user, apparently. Just dump it like that. Okay, so boot up Linux by default. Yeah, it does that. This is all comments and stuff on stuff you can do. But the part that you actually have to worry about if you're setting this up is where is your image, your kernel image. And so I have an image at /vmlinux. I don't know why that name is traditional. And we're going to label for it, and we're going to load it up read-only, and that kind of stuff. And then we got an init image right here. And this is also something you want to do if you're setting up Lilo. It doesn't have a good way to boot into your operating system if you change the kernel you told it about and update the boot sector, and then your kernel doesn't work. Because then you can't boot your operating system. And so it's traditional to leave your old kernel in there, just in case. Not necessarily required. Have courage. The new kernel will work. You can be sure of it. Okay. So Lilo was great. There's a few disadvantages of Lilo. First of all, Lilo doesn't support other operating systems besides Windows and Linux. And so that could be irritating if you had a FreeBSD system or installation, for example. And you could actually chain it. And that was one way to do this kind of stuff. So you'd end up with a separate boot sector right here. And so if you wanted to boot this operating system, when you were in this boot sector, what it would do is basically load this boot sector over it and start this boot sector running. And then you start whatever startup routine that operating system had. Well, in some cases, this could actually result in funny behavior. For example, suppose you got this bootloader and this bootloader configured, and this one has that one as an option, and this one has that one. You could actually go back and forth between bootloaders. And for a while, this is exactly how the computers were set up in the lab where I was an undergraduate. You had a Windows bootloader, and it was located in this kind of spot. And then you had a bootloader here to choose between Windows and Linux. Well, you could actually choose to go back from the Windows one, and so you could switch back and forth between bootloaders if you wanted to. That was great fun. Keep you entertained for 10 switches at least. Okay, so that's where the bootloader goes. Now this other one, Grub, Grand Unified Bootloader. It addresses that problem. You can boot FreeBSD directly out of Grub. And they excised Linux from the name of the bootloader because it's no longer associated with Linux necessarily. Linux is just one of many operating systems that the Grand Unified Bootloader can boot. And so it gives you this /boot directory. And Grub is going to be running on this machine right here. And back out of Nimrod, which actually is using Lilo. Okay. So on /boot here we have a series of kernels, all of vmlinux is over there, and resulting configuration stuff for all of them, the init images for all of them. Then we go to this directory grub. Okay, and should have here it is. .config. Okay, and so grub has a way to configure it in a text file here. Now, here's the thing about grub. You don't have to update the boot sector when you replace a kernel. Grub can actually look on the file system in this /boot location and find you a kernel. And so that's kind of handy. That does mean that Grub is a lot more complicated bootloader than Lilo is. Lilo has no understanding of the file systems for A or B here. And so Lilo can't look inside the file system and find something for you. Grub can. Okay. So that's the difference there. And so you don't have to rerun rewrite the master boot record on your computer when you use grub, because it can go find your kernel inside the file system. Now, there is one thing weird about grub. For reasons I don't quite understand, they refer to hard drives in a different way than they do in Linux. And so in Linux, your drive will be like dev SDA or something like that. And in grub, it'll be like HD, and then in parentheses, you got two numbers. I always have to look up what the two numbers mean and how to figure out what the hard drive is. And anyway, that's fine. I think I should have just copied Linux, because most of the people that use grub also use Linux, but they didn't. Okay. Yes, there goes impossible. Sure. Okay. So either way, regardless of what your bootloader is, the basic problem here is the kernel needs to be put into main memory and started running. And a lot of the time, the kernel is stored compressed in the it makes it smaller. Why not? I guess. Okay. So here's where we start our course textbook. Our course textbook, I kind of like it in a way, but I have to admit, it is a little bit difficult to read in some ways. The English is a little bit subpar in parts, but it's possible to decode. And the author is very thorough. There's not a lot of broader context given, but it definitely goes through it piece by piece and covers it well. I was kind of pleased by it. Okay, I went ahead and put the Linux 0.11 source code on here. And so if we go, or on this one, on the top there. So if we go to user src, we got Linux source 0.11 in addition to 3.6 and 3.2. If we go to the Linux source here, we'll find it delightfully simple. So, for example, in the boot directory, and we're about to talk about boot, we have 3 files here. They're all written in assembly. This is the contents of the boot sector that go in that boot place on the drive there. This one does some setup in terms of getting the kernel ready to go. And this is the preamble to the kernel, basically the first part of the kernel. And it gets run before the kernel. It gets stuck at memory location 0. And actually gets overwritten after it's in memory, after it's been run. And it's not needed anymore. Anyway, so you got just kind of 3 here. In order that they run in would be boot sect, and then setup, and then head. And then after that, we're into the kernel. Okay, kernel proper, not just a header for it. Now see the boot directory for 3.16. Okay, so the first thing you notice is not here. That's because how you boot a machine is dependent on the architecture. Linux 0.11 works on x86 processors. Linux 3.16 works on a wide variety of architectures. So if you go to Arch here, there you have them. So if you're using it on your phone, you're going to be using ARM or ARM64. And it's a completely different boot up procedure than if you're on a desktop computer and you're using x86. Okay, so if we look in here, we've got the architecture-specific parts of the kernel, and now we have boot. And it's got some C and some assembly, and totals 5,293 lines. And there's a lot more that goes on here. Okay, so now you can see what our settings online is. That shows you all the concepts without making it too difficult. Okay. Okay, so this is what goes into the boot sector. Copyright 1991. Maybe I want to talk about interrupt service routines real quick first before we get into that. So the interrupt service routines. Whenever you do stuff on a computer that ends up interrupting the CPU, an interrupt service routine is required. So if I move this mouse, this is a USB mouse. It won't generate an immediate interrupt. If it was plugged into a PS2 port, it would. And the keyboard is actually the same way. With USB, the USB system, it works by polling. Basically, it polls and generates interrupts later. Traditional keyboard, when you push a key, you get an immediate interrupt. And so something has to handle these interrupts. And initially, the BIOS actually provides interrupt service routines, code that should be run when an interrupt is called. And so that's there initially. Okay. And the BIOS has an interrupt, number 19, You see this quoted as 19H a lot, which just means 19 in hex. And you see 0x19H, which to me seems dreadfully redundant because 0x means it's a hex number. Anyway, so interrupt 19 loads the sector from a drive into memory. And so that can get things started. Okay, so let's go back over to this source code over here again. And it mentions boot sect S is loaded at 0x7C00 by the BIOS startup routine. So when BIOS calls interrupt 19, it copies sector 0, track 0, basically the very first part of the disk to this location in memory, 7C00. Now, notice that this is a 16-bit address. Well, at this point, the processor is running in real mode. And real mode on Intel CPUs, Intel x86 CPUs, is compatible with the 8086 processor. And 8086 was developed from 8008, and it's been with us since the early part of the 80s. And so, even on a modern system, actually, the Intel CPUs start up in real mode, and they have 16-bit addresses. There's extended 20-bit addressing, which will start getting used pretty much right away. And 20-bit addressing gives you a megabyte maximum of memory. Okay, so that's how these things wake up. Okay, so anyway, it goes ahead and gets located to this spot, and it mentions that bootsect moves out of the way. I put a note in here that it goes unwillingly into 0x7C00. I don't know about that. There's not really free will among software here, but it certainly is not where Linus wanted it. It's where the BIOS put it, and it puts it there by convention. So one of the first orders of business is to copy itself somewhere else, because the memory early on there is going to get used for something else. Okay, and then setup gets loaded after itself. And then the system gets located at that address. Okay, and he has some notes about calculation and how long things are. I should mention briefly what Minix is here, since it's going to be referred to occasionally in the source code. This is a system developed by Andrew Tenenbaum, the guy who wrote the textbook we use for CS250. And he wrote it as a teaching operating system so that people can study it as a simple operating system. If this class were being taught in 1991, we would be looking at Minix right now. And so it was a reasonable teaching operating system. Incidentally, there were allegations later that Linus had copied a bunch of stuff from Minix into Linux. And so that Tenenbaum ought to have some kind of copyright. And Tenenbaum himself was like, no, he didn't copy it. Minix was way better. Anyway, yeah, Minix is there. It's like, you should have copied it. It's funny. Okay, so anyway, okay, so it's, but anyway, Linus definitely had the Minix source code when he was doing this and studied it, and so it has some design considerations that are probably more or less inspired by the other one, even if it's not the same code. Okay. Laying out where exactly stuff is going to be in memory, and we ourselves are going to be at 0x9000. Did I miss anything I was supposed to say? No, not really. Well, I did. I'll go back and get it real quick. Okay. So, the BIOS loads this stuff to 0x7C00, and then this stuff that gets loaded gets moved. Well, this whole program here will start an operating system going. That's not strictly required. I mean, we could have put something else there. You could have just taken your C program and you say, well, we're going to go ahead and compile this, and we're going to put it on disk, and then we're going to make a bootloader for it so that when we start the computer, it'll go ahead and get our program to run, and then the results are going to come out of the printer, and then the computer's going to shut down. And so you can actually run things that way, 60s style here. There's no reason that wouldn't work. Okay, so there's nothing really special about the operating system. It's just a program. It goes in there and manages their programs. Okay. So stuff is located there, but we're about to move to this location here, 0x9000. We can move here. It's actually pretty well commented. So that actually happens right here. The weird thing is, you kind of jump from like this line to this line, and at the same time move from memory from the 0xC whatever up to 9000, which actually will start running the next line of code, even though it's jump into a different segment. Basically, we're jumping to go in the init seg, which is 0x9000, and so we go to go in init seg, but we actually already copied there everything from the boot sector up to that location, and so we end up starting off at the very next instruction, which I thought was kind of cool. A lot of clever stuff in the kernel. Okay, so I want to mention a couple other interrupts here. They get used later. You can see ints here, interrupt 0x13, interrupt 0x13, and a bunch of 13s. Later you see interrupt 10. Well, this is calling the interrupts on a CPU, and then you're going to get the BIOS interrupt service routine. Because once the interrupt's called, some code has to process it, and that's going to be the stuff that BIOS has put there. We haven't replaced it with anything of our own. It's still just standard there. Okay, here's what these things do. So 13 loads a specific sector to a specific location. I shouldn't say 13, it's in hex, so actually it's bigger, 19 in decimal, and that one's 25. And that one's 16. Anyway, you get the difference. You've been around this so long enough. Okay, so we load a specific sector to a specific location. And so this is a little bit more flexible than the interrupt 19 hex that just loads the boot sector in a particular location. So whenever you see an interrupt 0x13, it means that we're taking something off the disk and sticking it into memory somewhere. 0x10 is BIOS interrupt for video services. And so that's used to print stuff out here. Stuff like, inane messages. And so that's what you're looking at whenever you see a 0x10. Now, before any of these interrupts can be called, the CPU registers have to be set up just so in order to make it happen. So you're in DX, we're going to put a 0, drive 0, head 0, and sector 2, and so that goes into CX and that kind of stuff. And this brings up the question, how did Linus know he's supposed to put these things in these registers? Well, there's a guide for it, x86 instruction set reference. And my guess is he had a copy of this thing, but it's available online too. And so you can go and look at basically what does the x86 CPU do when it's given each of these different instructions. And it's got a, that's what it does. Okay, so you just study the processor. The processor is a simple gadget. It does exactly as it's told, and you can figure out what it does from that. Incidentally, for a good while at least, I don't know if they still do it, if you had an Intel processor and you sent them a note and said, well, I have your processor and I'm trying to program for it, but I need documentation on which instructions it accepts and what it does when you send it the instructions. They'll mail you like a set of 4 encyclopedia-sized volumes that explained what the CPU would do when presented with different inputs. And so from there, a friend of mine got the set because he was writing his own operating system, just like for fun. He was a programmer, and so when he goes home, I guess he gets, things are different. And so he makes them the same by writing his operating system. Anyway, whatever. He's writing his operating system, and so he needed the reference. Okay. So that's how you figure out what these things do. And these days Google is an invaluable tool in that too. But I just saw the reference online. Okay. So as far as what we're doing here, general goals. We want to get the next program loaded. So if you look at here, we got this setup.s. And so this is going to get run next. And so we need to get this into memory. So load setup here. Load the setup sectors directly after the boot block. And so you can go ahead and copy. Remember, 0x13 takes a specific section, loads it to a specific spot. Okay. There we go. Okay, print name messages, etc. Figuring out which root device to use. So you can have more than one hard drive and such in a system, and you can have different types of drive too. And so this distinction right here, this is historical. You remember the little floppies held more than the big floppies, like the plastic 3.5s would actually hold more than the floppy 5.25 ones, which held 1.2 megabytes. Anyway, it's becoming important at this point in the program to figure out what exactly the geometry is on the disk we're using, so we know which sector to request to have loaded. And so there's a bit of work done here to figure out what kind of drive are we actually on, so that we can do the loading routines and load the system segment here to 0x a bunch of zeros. You can also see there's these calls here. Call basically gives you a function in assembly. So we're calling kill motor. If we scroll down to the bottom here, we should have a definition. Here's kill motor. And so apparently this is how you turn off the floppy drive motor on an IBM compatible system with an Intel processor. You push something in a particular register, and anyway. So out B is going to be out bus. Anyway, it sends a instruction to the floppy drive to turn itself off apparently. Okay. Now, you notice that the register names here, like if you had CS250 and still remember anything about x86 from it, which is only going to include some of you, because before I was teaching 250, we studied some other architecture, or well, other people than me studied some of their architecture. And anyway, so on Intel CPUs, DX here, the name that we're using right up there, is a 16-bit register. EDX is 32 bits, stands for extended DX. That was great until we got the x86-64 processors, and now we have RDX, which, I mean, you can't use E again. E was already used, and so R, I guess, means even more extended than E did. And so depending on whether you're talking about a 16-bit, 32-bit, or 64-bit number, you might use a different version of the register name. Now, on a modern CPU, when you go use DX, it does mean you're using 16 bits of the end of a 64-bit register and leaving the other 48 unused. But that's fine. I mean, we're just trying to get the silly thing running anyway. Okay, so that turns off the motor. Print out a message here. Loading system. That was probably the inane message, I guess. Does it say MSG1 up here? Print some inane message. I don't see it. Read cursor position. No, whatever. Anyway, oh, there it is. MSG1. So, yeah, we're printing out loading system. Okay, so we try and get the segment located up there, and this is mostly more functions. Oh, I forgot to show you how that function finishes. So we got ret there, and that means return back to where we came from, basically. Pop a frame off the stack. And so these are other functions that do stuff relating to floppy control for the most part. Read a track off the floppy. And, yeah, okay. Oh, I'm out of time. Anything in particular I need to say to wrap this thing up? I guess I should check. We'll talk about setup.s next time. And turning off interrupts and replacing them, and that kind of stuff. Reprogramming interrupt controllers. Okay.